This is the summit of the Greenland ice cap. The ice here contains a frozen record of the planet's changing climate. As they drill into the polar ice caps, scientists travel back in time, returning to the surface ice formed from snowflakes that fell hundreds of thousands of years ago. These ice cores were drilled by the Russians at their Vostok research station in the heart of Antarctica. They can take scientists back more than 400,000 years. For climate scientists like Jim White, the most valuable thing to come out of the ice is a record of the Earth's atmosphere as it was in the distant past. The deeper the ice comes from, the older it is. Trapped within it are air bubbles, tiny samples of the atmosphere preserved from the time the ice formed. But the cores are doubly valuable because they also contain a record of temperature. By examining the composition of the ice crystals themselves, scientists can work out how cold the air above Antarctica was when the snow fell. The temperature record reveals a history of repeated ice ages, as the Earth has warmed and cooled in a 100,000-year cycle. This graph takes us from 400,000 years ago to the present day at zero. When the line is at its highest, the climate on Earth was similar to what we know today. When the line is falling, the Earth was sliding into an ice age. What lies behind these huge swings in temperature? When the level of the greenhouse gases carbon dioxide and methane are plotted alongside temperature, the answer becomes obvious. The similarity in the curves is truly astonishing. The ice core record shows that changes in the level of greenhouse gases have been intimately related to changes in the climate for at least 500,000 years. But what causes the level of carbon dioxide to rise and fall so dramatically? For Peter Cox, the answer is clear.
Well, because this is a period long before we started to emit from fossil fuels, these have to be natural changes in the carbon cycle. So what you're really looking at here is carbon moving in and out of natural stores in the Earth system. So if there's more carbon in the atmosphere, it implies there was less carbon in either the ocean or the land, or both. So what we're really seeing here is the natural tendency for carbon to shift from these various stores.
Natural processes such as the growth of the Amazon don't just store huge quantities of carbon, they also release it. What's more, they can do so very quickly.
We also see in these ice cores some really astounding climate changes. We see temperature increases of 20 degrees centigrade in less than a human lifetime. And we see that occurring many times in the past. It tells us that there are sensitive spots in our climate system. And when we pass one of those sensitive spots, one of those thresholds, that we can expect some really huge climate changes in very short periods of time.
During the ice ages, the level of CO2 oscillated between 170 and 280 parts per million as carbon moved in and out of natural stores. Today, levels stand at 370. So far, natural stores of carbon have been growing, helping to slow global warming. But as temperatures rise, are we about to cross a threshold where these stores would start to release? Today, the rainforest is absorbing carbon because the growth of trees is outstripping the rate at which dead trees decay. But occasionally there is an unusually dry year and many trees die. Measurements suggest that in these dry years, the forest can temporarily give out more carbon dioxide than it takes in.
That's because growth is suppressed because you haven't got enough water. But decay from the soil, which returns carbon dioxide to the atmosphere, carries on apace. So for a while, the decay beats the growth and you get carbon released to the atmosphere. What we find in the climate model is that that happens in the future as a permanent state. So the warming of the sea surface leads to a drying of Amazonia.
Okay, so the Amazon is the only place where you have really a quick change in...
As the climate warms, so weather patterns in the Pacific are changing. This is predicted to mean less rainfall in the Amazon basin. In Peter's model, this turns the forest from something that slows the rate of climate change into something that accelerates it.
At the moment, the system's buffering us from the effect of our emissions to some extent. But in the Amazon, although that happens for a while, it's predicted to be a sink by the model now. In the near future, it would become a source, if the model's right, because of this drying in the region.
And die back.
And die back, because once you dry the system, you can't actually support all of this diversity.
The short dry season in Amazonia means that the forest never has a chance to dry out properly. It remains damp all year round. But if the dry season were just a few weeks longer, like the savanna, the forest would become dry as tinder, and that would make it vulnerable to its deadliest enemy.
A savanna naturally burns twice in a decade.
And that's what keeps it from becoming a forest, I suppose.
Yes, absolutely. When the soil becomes very dry, then the forest becomes dry and flammable, so fire becomes a risk. The forest becomes too dry during the dry season, then fire might happen, and the fire really kills most of the forest species. And then in that area we might see savanna. Of course, the savanna vegetation as a whole has much less carbon in its stock. The forest has perhaps 5 to 10 times more carbon in stock. So the end result would be a pulse of carbon into the atmosphere when the forest is replaced by the savanna.